the star that is already behaving like it's dying. Step outside tonight, find Orion. You know the shape, the belt, the shoulders, the familiar geometry that has been hanging in winter skies since before human civilization had a written language. Now look at the upper left corner of that constellation. There is a reddish star sitting there, dim enough to overlook, familiar enough to ignore. That star is behaving in ways that have never been recorded in the history of astronomy. In the last 5 years, it has done 3 things that broke scientific models. It dimmed to the lowest brightness ever measured in over 150 years of systematic observation. Then it physically threw a piece of its own surface into space in an event so far outside existing science that researchers had to invent a new category just to name it. Then it swung in the opposite direction entirely and reached the brightest level ever recorded. Right now, at this moment, professional astronomers around the world are pointing instruments at that star on a continuous basis. Not occasionally, not as part of a broader survey, continuously. Coordinated monitoring programs spanning multiple continents and multiple wavelengths of light-generating data streams that are being actively analyzed in real time. They are not calm about what they are seeing. This is not a story about something that might happen in a distant theoretical future. This is a story about a star that is doing something right now, something that the scientific frameworks built over decades were not designed to explain, and something that carries an implication so strange it takes a moment to fully absorb. The light you are seeing when you look at that star tonight left it roughly 700 years ago, the medieval period on Earth. The actual present-day star, what it looks like right now in the real universe at this exact moment, is something you cannot see, something no human can see, something no instrument on Earth or in orbit can reach, because the information about what that star is doing right now will not arrive here for another 700 years. Which means Betelgeuse could have already exploded. Not might explode. Not is going to explode someday. Could have already exploded. The light from that explosion could be traveling toward us right now, 700 years into a journey that ends the moment it hits Earth's atmosphere and the sky above Orion changes forever. Or the star is still there, still pulsing, still recovering from everything it has done to itself recently, still burning through its remaining fuel toward an end that could be centuries away or 100,000 years away. Nobody knows. And that uncertainty is not a failure of science. It is a confirmed physical reality of how light moves through space and time. What we do know is this: Betelgeuse is one of the most extreme objects in our galaxy. It is confirmed to be approaching the end of its life. It has recently demonstrated behaviors that no star in recorded astronomical history has demonstrated before. And when it finally goes, it will produce the most scientifically significant event in the history of human observation of the sky. The closest comparable event in the modern era happened in 1987. A star exploded in a companion galaxy roughly 160,000 light-years away. It was visible to the naked eye from the southern hemisphere. It generated more scientific data than almost any other single astronomical event in the 20th century. Researchers still publish papers about it today. Betelgeuse is 200 times closer than that. What is coming, whether it comes in a human lifetime or in geological time, is not comparable to anything that has happened before in the age of modern telescopes. And the story of what Betelgeuse has already done, what it is doing right now, and what the instruments watching it are listening for, is one of the most remarkable stories in contemporary science. We are going to cover all of it. We begin with scale, because before you can understand why scientists are not calm, you have to understand what Betelgeuse actually is. And that requires confronting a number that the human brain is genuinely not built to process. What Betelgeuse actually is. The word supergiant does not prepare you. Neither does the word massive. Neither does any single adjective in the English language applied to a star. So instead of starting with adjectives, we are going to start with a comparison that has been verified by decades of measurement and confirmed by direct telescopic observation. Picture a standard American football stadium, the kind that holds 70,000 people on a Saturday afternoon. Now, picture a single orange sitting in the center of that stadium, placed exactly at midfield. One orange, surrounded by 70,000 empty seats and the vast open space of the stadium around it. The orange is our sun. The stadium is Betelgeuse. That comparison is not poetic license. It is not an approximation designed to sound dramatic. It reflects the confirmed ratio of sizes between our star and Betelgeuse as measured by direct imaging and decades of spectroscopic observation. The volume of Betelgeuse is so large that if you hollowed it out and filled it with copies of our sun, you could fit roughly 700 million of them inside. 700 million suns inside one star. Now take that comparison and apply it to something you know. Our sun is large enough that if it were hollow, you could fit roughly 1.3 million Earths inside it. Most people find that number already difficult to absorb. Multiply it by 700 million and you have Betelgeuse. The physical size translates into something even more striking when you place Betelgeuse where our sun currently sits. If you picked up Betelgeuse and dropped it exactly at the center of our solar system, its outer surface would extend outward past Mercury, past Venus, past Earth, past Mars, and keep going until it swallowed Jupiter's entire orbit. Everything you know as the inner solar system, every planet you could name as a child, every world that has been visited by a spacecraft, every place in our solar neighborhood where life has ever existed would be inside the star. Not near it, inside it. The Earth would be gone, not destroyed by proximity, actually absorbed, existing within the body of the star itself. This is confirmed science, not theoretical, not estimated within a wide margin of error. Confirmed by direct measurement of Betelgeuse's angular size combined with precise distance calculations, the star is real, the measurements are real, and the implication that a single star in our galaxy could contain the entire inner solar system within its volume is simply what the numbers say. Now here is where Betelgeuse gets genuinely strange. Despite that volume, despite that absurd physical size, Betelgeuse weighs only about 10 to 20 times more than our sun. Not 700 million times more, not even 1,000 times more. Somewhere between 10 and 20 times more. Think about what that means. An object large enough to swallow Jupiter's orbit weighs roughly the same as 15 of our suns. The density is almost incomprehensibly low. The outer layers of Betelgeuse are not dense plasma the way the interior of our sun is. They are something closer to a vast, glowing fog. Thin, extended, tenuous. More like a cloud with heat than a solid object with weight. The star is not dense. It is immense. Those are very different things. Red supergiants get this large because they are bloated. The nuclear reactions happening deep in the core generate enormous outward pressure. That pressure pushes the outer layers away from the center. Over millions of years, those layers have expanded outward to their current extraordinary size, while the core at the center has remained comparatively small and dense. The star is like a balloon that has been inflated to extreme size around a small, dense center. Most of the volume is air. Most of the mass is core. That structure is directly connected to why Betelgeuse is red. Color in stellar physics is a temperature reading, a direct, unambiguous measurement of how hot the surface of a star is. Hot stars emit most of their light at short wavelengths blue, ultraviolet. Cooler stars emit most of their light at longer wavelengths orange, red. The surface of our sun burns at around 10,000 degrees Fahrenheit, which pushes its emission toward yellow-white. The very hottest stars in the galaxy burn at 50,000 degrees or more and glow blue-white with intense ultraviolet output. Betelgeuse's surface runs at around 6,000 degrees Fahrenheit. For a star, that is cool. Cool enough that the color shifts all the way to red. Cool enough that molecules, actual chemical molecules, can survive in the outer atmosphere without being torn apart by radiation. Cool enough that the star looks, when you find it in Orion on a clear night, distinctly warmer in tone than the stars around it. That reddish glow is not decoration. It is a temperature reading telling you that the surface of this star has expanded and cooled to a point that marks it as old. And old, for a star like Betelgeuse, has a very specific meaning. Our Sun has existed for roughly 4.6 billion years and is approximately halfway through its expected lifespan. It will continue burning hydrogen in its core for another 5 billion years before it begins to change. On cosmic timescales, our Sun is middle-aged, comfortable, stable. Nowhere near the end, Betelgeuse has existed for somewhere between 8 and 10 million years. That sounds like a long time. By human standards, it is an incomprehensible span. But on stellar timescales, it is nothing. Our Sun will outlive Betelgeuse by a factor of nearly 1,000. The reason is simple and brutal. Massive stars burn hot, and they burn fast. The more massive a star is, the more gravitational pressure it exerts on its own core. The higher the temperature at that core, the faster the nuclear reactions run, and the faster the fuel gets consumed. A star 15 times the mass of our Sun does not live 15 times as long. It lives 1,000 times shorter. Betelgeuse made a deal with physics when it formed. It got to be enormous. In exchange, it got almost no time. That time is almost up. The star is in the final stages of its life confirmed. Not speculated, not estimated with large uncertainty, confirmed by everything we know about stellar evolution applied to a star of Betelgeuse's mass and current state. The only question is how final the final stages actually are. Whether we are talking about the last chapter or the last paragraph or the last sentence, and that question leads directly to the events of 2019. Because in October of that year, Betelgeuse began doing something that had no entry in any existing scientific framework. Something that started slowly, built over months, and ended with researchers realizing they had witnessed an event with no name, no precedent, and no model to contain it. October 2019. The brightness measurements coming in from Betelgeuse begin to look wrong. Not dramatically wrong at first, just slightly off from expected values. The kind of deviation that might be noise, might be instrument error, might be a temporary fluctuation in the star's normal pulsation cycle. Astronomers keep watching. The deviation does not correct itself. It grows. Week by week through the autumn of 2019, Betelgeuse fades. The numbers drop steadily, consistently, in a direction that has no match in roughly 150 years of reliable brightness records. By November, the deviation is large enough that professional astronomers are taking targeted measurements specifically to track it. By December, it is the dominant topic in stellar physics discussions worldwide. By January 2020, it is in the news. By February 2020, Betelgeuse had faded to approximately 60% of its normal brightness. For a star that has been one of the 10 brightest objects in the night sky for as long as humans have been recording the sky, this was visible, not just measurable by instruments. Visible to the naked eye on a dark night, people who had looked at Orion their entire lives were noticing that something was different in the upper left corner of the constellation. The star that was supposed to be a bright reddish anchor of winter skies was dim, noticeably, undeniably dim. Amateur astronomers confirmed it first. Their reports flowed into variable star databases, maintained by organizations that have been collecting exactly this kind of observation for over a century. The data aligned. The dimming was real. Professional observatories confirmed it next. Spectroscopic measurements, photometric readings across multiple wavelength bands. Every instrument said the same thing. Betelgeuse was fading in a way that had no precedent in any recorded data. Then the question spread beyond the research community into every news outlet covering science. Is Betelgeuse about to explode? The question was not unreasonable. Betelgeuse was known to be a late-stage massive star. Late-stage massive stars explode. Watching the star fade rapidly and dramatically felt like watching the opening act of something enormous. Social media filled with supernova speculation. Scientists cautioned patience. The dimming continued. By the time it bottomed out, Betelgeuse had set a record, the lowest brightness measurement in over 150 years of systematic observation. That record still stands. Then, slowly, through the spring of 2020, the brightness began to recover. The numbers climbed back. By summer, Betelgeuse was approaching something resembling its pre-dimming levels. The recovery ruled out the supernova hypothesis definitively. A supernova would have blazed, not dimmed quietly, and then recovered. Whatever had happened, it had passed. But that left the harder question completely open. If Betelgeuse was not dying, what had just happened? The scientific community ran 3 hypotheses simultaneously throughout the investigation. The first was supernova, ruled out by the recovery, set aside. The second was dust. Betelgeuse regularly sheds material from its outer layers through stellar winds. That material can cool as it moves away from the star's heat and condense into tiny solid particles. A cloud of dust drifting between Betelgeuse and Earth would block some of the star's light, dimming it from our perspective without anything actually changing on the star itself. This hypothesis was physically plausible, consistent with known behavior, and required no new physics. For many months, it was the leading candidate. The third hypothesis was a temperature drop on the visible surface. Betelgeuse has enormous convective cells moving through its outer layers, massive bubbles of hot plasma rising from the interior and cooler material sinking back down. If a particularly cool cell had rotated into prominence on the side facing Earth, it could lower the average brightness without requiring any ejection of material. 3 hypotheses. Every available telescope pointed at Betelgeuse across every wavelength. Ultraviolet readings from space. Infrared measurements tracking heat signatures. Radio telescope observations of molecular emission in the outer atmosphere. The star was being taken apart data point by data point. Then the Hubble Space Telescope delivered its ultraviolet readings, and everything changed. The ultraviolet data showed that just before the dimming began, there had been an enormous outward movement of material from the star's surface, a surge. Something had pushed a massive quantity of material upward and outward from the photosphere with extraordinary force. That material had then traveled away from the star's intense heat, cooled as it moved, and condensed into exactly the kind of dust cloud the second hypothesis had proposed. So, the dust was real, but the dust had a cause, and the cause was violent. Something had erupted from the surface of Betelgeuse. Something large enough that the resulting dust cloud dimmed one of the brightest stars in the sky as seen from 700 light-years away. The cold patch that appeared on the surface during the dimming was not a convective cell rotating into view. It was a scar. The mark left on the surface after an enormous amount of material had been violently removed from that exact location. In 2022, a team of astronomers published findings that gave the event its name: a surface mass ejection. The outer layer of the star, the photosphere, the visible surface, had been physically ripped away in one enormous chunk and launched into space. Not plasma flung by magnetic fields, not gas gradually streaming away in a stellar wind. An actual piece of the star's own surface, torn off, thrown outward, cooling into dust as it traveled. The physics behind this had no parallel in any prior observation of any star. The models that existed before 2019 did not include this possibility. The frameworks built to describe how stars shed mass had no entry for a star physically throwing away a chunk of its own skin, cooling it in flight, and turning it into a dust cloud large enough to dim itself from across 700 light-years. A new category of event had been created, observed once, on Betelgeuse, with no comparison point anywhere in the history of stellar astronomy. Our sun produces eruptions. They are called coronal mass ejections, and by any standard applied to human experience, they are catastrophic events. The largest ones we have ever measured carry the energy of billions of nuclear weapons. They fling billions of tons of charged plasma outward at millions of miles per hour. When they are directed toward Earth, they can disrupt satellite communications, damage power grid infrastructure, and produce auroras visible from latitudes that never normally see them. The largest coronal mass ejection in recorded history, the Carrington event of 1859, was powerful enough that telegraph systems across Europe and North America caught fire from induced electrical currents. Operators reported receiving shocks from their equipment. Some telegraph systems continued operating even after being disconnected from their power sources, because the induced current from the geomagnetic storm was sufficient to drive them. If an equivalent event struck Earth today, the damage to interconnected electrical infrastructure would be measured in trillions of dollars, and recovery would take years. That is the largest coronal mass ejection we have ever recorded from our Sunday. The surface mass ejection from Betelgeuse released somewhere around 400 billion times more mass. Read that number again, 400 billion times, not 400 billion times more energy, 400 billion times more mass. The physical material ejected from Betelgeuse's surface in this single event was 400 billion times greater than the largest eruption ever recorded from our own star. There is no intuitive comparison that makes this scale accessible to the human brain. The numbers involved are genuinely outside the range of anything evolved cognition was designed to process. But we can try to approach it from a different direction. The mass ejected from Betelgeuse during the Great Eruption was estimated at several times the mass of our moon. Our moon weighs approximately 730 quintillion tons. Several lunar masses worth of stellar material ripped from the surface of a star and launched into space in a single event. Imagine the moon, not as a distant object in the night sky, but as a physical mass, something large enough to be visible from 240,000 miles away, something whose gravitational influence produces the tides of every ocean on Earth. Something that took the Apollo program, the most ambitious and expensive peacetime engineering effort in human history, to reach. Now imagine several of those worth of material torn from the surface of a star and thrown into space, not gradually, not over millions of years of stellar wind outflow, in a single event, one eruption, one chunk, gone. The material was not a solid rock, of course. It was super-hot plasma stellar gas moving outward at hundreds of miles per second, laced with heavier elements forged in decades of nuclear burning in Betelgeuse's outer layers. As it moved away from the star's intense heat, it began to cool. The cooling caused molecules to form. The molecules clumped into tiny solid particles. Those particles became dust. The resulting cloud was enormous. Astronomers tracked it using infrared telescopes because dust absorbs visible light and re-emits it in the infrared, the same reason a cloud of smoke or ash glows faintly orange in firelight. The cloud's temperature, composition, and movement allowed scientists to calculate backward in time and determine exactly where it came from and when it was ejected. And what those calculations revealed added another layer to the story. The dust cloud was not distributed evenly around the star. It formed primarily on one side, the same side that showed the cold scar on the surface. The ejection was directional, not a global shedding of the outer layers, but a localized event. One specific region of the photosphere, one concentrated burst of material launched outward in roughly one direction. From Earth's position, that side was facing us. Think about what that means. The ejection was asymmetric. It came from one part of the star. If that part had been on the far side of Betelgeuse, pointed away from Earth, the dust cloud would have expanded away from us, and we would have seen almost nothing. The brightness drop would have been minimal. The event would have passed undetected by almost every instrument on the planet. We witnessed the great dimming because we happened to be in the right position. The chunk of surface that was ejected happened to be the chunk facing Earth. The dust cloud it produced happened to drift between the star and our line of sight. And this introduces a thought that the researchers who published these findings were explicit about in their papers. If Betelgeuse has done this before in previous centuries, in previous millennia, and those ejections were pointed away from Earth, we would have no record of them. The Great Dimming might not be unprecedented in the history of Betelgeuse. It might just be the first one we were positioned to see. Scientists went back through historical brightness records looking for evidence of earlier, unusual fluctuations. The archives, maintained by variable star observers, stretch back over a century. Further back, historical records from astronomers across multiple civilizations document Betelgeuse's appearance across more than 2,000 years. The analysis of those records found hints at unusual variations that could represent earlier, smaller eruptions, or could simply represent the normal pulsation behavior of a turbulent star. The data is ambiguous. The debate is ongoing. No definitive earlier surface mass ejection has been confirmed. But the possibility that these events are a recurring feature of Betelgeuse's behavior, not a singular, unprecedented occurrence, but a pattern, has permanently changed how researchers classify the star. Betelgeuse is now understood to be more dynamically violent than any model built before 2019 assumed. And the dust cloud from that violence is still out there right now, still moving, tracked by infrared observatories watching it drift outward, cool, and slowly disperse into the surrounding space. It will not reach Earth. It is moving away from us, not toward us, expanding outward in the direction it was launched. In thousands of years, it will have dispersed enough to become part of the general material surrounding Betelgeuse. In millions of years, it will contribute to the interstellar medium, the sparse material filling the space between stars, eventually becoming part of the raw material from which future stars and planets form. That last point is worth pausing on. The dust cloud produced by Betelgeuse's eruption, the specific material that dimmed the star from 700 light-years away and puzzled astronomers for months, will one day, in the deep future, be incorporated into new worlds. The atoms currently drifting outward from Betelgeuse were forged in the star's interior over millions of years of nuclear burning. They have been part of one of the most extreme objects in the galaxy, and they are now beginning the long journey toward becoming raw material for whatever comes next. Betelgeuse is not just behaving strangely, it is actively seeding the galaxy. But the eruption that produced that cloud did not leave the star unchanged. The photosphere was altered. A region of the surface had been physically removed. And what happened to the star's internal rhythms in the months and years following the ejection revealed something even more unsettling about where Betelgeuse currently stands in its life cycle. Because after the great eruption, the star's heartbeat broke. And when it came back wrong. Every living thing has a rhythm, a pulse, something that repeats at a measurable interval and tells you simply by continuing that the system generating it is still functional. For Betelgeuse, that rhythm is its pulsation cycle. And for over a century, astronomers treated it the way a doctor treats a patient's heartbeat, as the single most reliable indicator of the star's internal condition. The pulsation works like this. Deep inside Betelgeuse, nuclear reactions generate enormous outward pressure. That pressure pushes against the weight of the entire star, pressing inward. The outer layers respond by expanding outward as the pressure builds. But as the layers expand, they cool. Cooling reduces the pressure that drove the expansion. The outer layers then fall back inward, compress, heat up again, build pressure again, and the cycle repeats. On Betelgeuse, with its outer envelope stretching hundreds of millions of miles, a single cycle takes months and years to complete. Betelgeuse has 3 overlapping pulsation cycles running simultaneously. The primary cycle runs approximately 420 days, just over a year. This is the rhythm driven by the pressure dynamics of the outer envelope, the expansion and contraction of the star's bloated outer layers, responding to the energy pushing up from below. Astronomers had tracked this cycle for well over a century. They could predict where Betelgeuse would sit in its brightness range months in advance simply by knowing where it stood in its 4-2-0 day rhythm. The second cycle runs somewhere between 5 and 6 years. The third runs approximately 12 to 17 years. These 3 rhythms overlapped and interacted, producing a pattern of brightness variations that was complex but not chaotic. Researchers who had spent careers studying Betelgeuse could read that pattern, the way a musician reads a score. The individual rhythms were recognizable. The combined output was predictable within known margins. That predictability was the baseline. And baselines matter in science because they are what you measure deviations against. After the Great Eruption of 2019 and 2020, the baseline broke. The primary 420-day cycle went quiet in a way that had no entry in any previous record. The expected brightness peaks failed to arrive on schedule. The rhythm's amplitude collapsed. Instead of swinging to predictable highs and dropping to predictable lows, Betelgeuse sat in a muted, uncertain middle range for an extended period. The drumbeat that had been ticking reliably for over a century of observation simply stopped ticking. The conclusion published by the researchers studying this was clear. The surface mass ejection had physically disrupted the pulsation mechanism. By removing a significant portion of the star's outer layers from one region of the photosphere, the eruption had altered the very surface that participates in the expansion and contraction cycle. The photosphere was thinner in the affected area. The pressure dynamics had changed. The mass distribution was different. The star's own heartbeat had been thrown off rhythm by an event the star itself generated. That kind of self-disruption had never been documented in any stellar observation before. The pulsation did eventually return, but when it came back, something was immediately apparent to every team tracking it. It came back wrong. By 2023, the data confirmed across multiple independent observation programs what the numbers had been suggesting for months. The primary pulsation cycle had settled into a new period, measurably different from the pre-eruption value. Not dramatically different. Not obvious to a casual observer, but confirmed by teams working in different countries using different telescopes, cross-referencing different historical archives. The 420-day rhythm that had been the star's most consistent drumbeat for over a century had shifted. The clock had been dropped and reassembled slightly wrong. The change made physical sense. The period of pulsation is determined by the physical properties of the outer envelope, its mass, its temperature, its opacity. The surface mass ejection removed material from those outer layers. Less material meant different opacity, different mass distribution, different pressure balance. The eruption rewrote the boundary conditions of the outer envelope, and the pulsation period adjusted to reflect the new physical reality. The recovery of that period, the slow creep back toward the original 420-day rhythm, as the photosphere rebuilds itself over years, is ongoing right now and being tracked in real time. But the recovery timeline carries its own uncertainties because there is no prior observed precedent to compare against. The models being used to estimate recovery duration are models that were built before the Great Eruption demonstrated that surface mass ejections could happen at all. They are being revised as new data arrives. Then in 2023, something happened that was completely outside the recovery model. Betelgeuse, which had recorded the lowest brightness measurement in over 150 years, just 3 years earlier, reached the highest brightness ever measured. Not recovered to pre-dimming levels, not returned to its historical average, exceeded every brightness reading in the entire 150+ year archive, set a new record at the opposite extreme from the record it had set during the dimming. Multiple observatories confirmed it simultaneously. The elevated brightness was sustained across months before beginning a gradual return toward more typical values. The duration ruled out a simple statistical coincidence. Something was driving Betelgeuse to an extreme it had never reached in the history of recorded observation. 2 readings of this surge exist in the published literature. The first is recovery overlapping pulsation rhythms, temporarily synchronizing into a combined output higher than any single cycle reaches alone. The star is healing. The second is escalation, a star whose interior is approaching its final burning stages, producing increasingly extreme swings in its outer layers. Record low, followed by record high, is not recovery. It is a pattern of growing instability. Neither reading is definitively supported over the other by current data. Both are consistent with what has been observed. The only way to distinguish between them is to keep watching, which is exactly what the instruments are doing. Everything visible about Betelgeuse is surface information. The pulsation, the dimming, the eruption, the brightness surge. All of it is the outer skin of the problem. What actually determines this star's fate is happening somewhere no telescope can reach. Deep inside, behind hundreds of millions of miles of stellar gas, in a region where temperatures and pressures make the surface seem mild by comparison. The interior of a red supergiant is layered like an onion, a series of concentric shells, each one burning a different fuel at a different temperature, each one piling pressure on the shell below it. To understand what is happening inside Betelgeuse right now, you need to understand each layer of that onion. Because the layer the core is currently burning is the single most important unknown in all of Betelgeuse science. Betelgeuse began its life fusing hydrogen into helium, the same process happening inside our sun right now. Hydrogen fusion is the fundamental act of stellar existence, combining 4 hydrogen nuclei into one helium nucleus and releasing energy in the mass difference between them. That energy is what holds the star up against the inward crushing pull of its own gravity. For our sun, hydrogen fusion will continue for another 5 billion years. For Betelgeuse, it lasted only a few million years. The star's enormous mass meant greater gravitational pressure on the core, which meant higher temperatures, which meant faster reactions, which meant the hydrogen was consumed in a fraction of the time our sun will take. When the core hydrogen ran out, the core contracted, heated, and ignited the next fuel. Helium. The ash of hydrogen burning became the fuel of the next stage. After helium came carbon. After carbon, neon. After neon, oxygen. After oxygen, silicon. Each stage runs hotter than the previous one. Each stage runs faster. The time scales compress dramatically with every transition. Hydrogen burning lasted millions of years. Helium burning lasted hundreds of thousands. Carbon burning lasts roughly 1,000 years. Neon burning lasts about a year. Oxygen burning lasts months. Silicon burning lasts days. Read that again. From millions of years down to days, the same star, the same fundamental process. But the timescales collapse by orders of magnitude with each successive stage, because each new fuel is harder to ignite, burns hotter, and exhausts faster. At the end of silicon burning, the core fills with iron, and iron is where everything stops. Every fuel that has burned inside Betelgeuse from hydrogen through silicon released energy because the products of fusion were lighter than the ingredients. That mass difference converted into energy. That energy held the star up. Iron breaks that chain permanently. Fusing iron does not release energy. It requires energy. The iron nucleus sits at the absolute bottom of the nuclear energy landscape. Once iron accumulates in the core, there is no fusion process that can extract anything useful from it. The core fills with iron. Fusion at its edges keeps adding iron to the pile. The core grows heavier, denser, hotter. It cannot fuse its way out. The energy generation that has held the star up for millions of years is ending. When the iron core reaches roughly 1.5 times the mass of our sun, the electrons providing quantum mechanical resistance to compression can no longer hold their positions. They get forced into protons, producing neutrons and releasing a flood of neutrinos. The core, stripped of its electron pressure, collapses. In less than 1 second, a core roughly the size of Earth compresses to a ball roughly 12 miles across. A teaspoon of the resulting material would weigh 10 billion tons. The outer layers, still falling inward, slam into the newly formed dense core and rebound in a shockwave moving outward at tens of thousands of miles per second. The star tears itself apart. In the chaos of the expanding explosion, elements heavier than iron, gold, silver, uranium, platinum form for the first time. In its final moments, Betelgeuse becomes a factory for the heaviest atoms in the periodic table. This end is confirmed to be coming. The physics is settled. The only question, the most consequential unknown in all of stellar astronomy, applied to this specific star, is what stage of that sequence the core has currently reached. If Betelgeuse is still burning oxygen, it could remain stable for tens of thousands of years. If it has reached silicon burning, the end could come within years or decades. If the iron core is already forming and approaching its critical mass, The collapse could be close on any timescale that matters. Scientists have no direct way to observe which of these is true. The core is hidden behind hundreds of millions of miles of stellar gas. What researchers have instead are indirect clues filtered through the surface behavior. The pulsation disruption, the record brightness swings, the great eruption, each carries faint signals from the interior. Reading those signals correctly, extracting core information from surface measurements is one of the defining challenges of contemporary stellar astronomy. And the researchers doing that work do not agree on the answer. Some look at Betelgeuse's recent behavior and see a star whose surface is reflecting increasing turbulence from a core working through its final burning stages. Others argue the surface events are fully explained by the outer envelope's own dynamics and carry no reliable information about the core whatsoever. Both positions are published, both are peer-reviewed. Both are supported by credible researchers working from the same data. The honest answer to where Betelgeuse's core currently stands is that nobody knows. The most important variable in this entire story is hidden from every instrument humans have ever built. And inside that uncertainty lives the difference between a star with 10,000 years remaining and a star already lighting its final fuse. At some point, the iron core reaches its critical mass. The collapse begins, and the first thing that leaves the star is not light. It is a flood of neutrinos so intense that every detector on Earth would be simultaneously saturated within seconds of the burst's arrival. This is the warning, and it comes hours before anything changes in the sky. Neutrinos are among the strangest particles in existence. Almost no mass, no electrical charge. They interact with normal matter so weakly that one can pass through a light year of solid lead without hitting anything. They stream through your body right now, at roughly 100 trillion per second, produced by our sun, and you feel absolutely nothing. During the core collapse of a massive star, the collapsing material briefly becomes so dense that even neutrinos are temporarily trapped. Then, they punch through in a burst carrying away approximately 99% of the total energy released in the collapse. At 700 light-years, that burst washes through Earth, through every person and building and mountain and ocean, mostly undetected, but not entirely. Physicists built underground detectors specifically to catch neutrinos from exactly this event. Located deep underground to shield them from cosmic ray noise, these facilities contain enormous tanks of ultra-pure water, surrounded by thousands of sensitive light detectors. When a neutrino occasionally interacts with a water molecule, it produces a tiny flash. The detectors record that flash. Under normal conditions, they catch a handful of neutrinos per day from our sun day. The 1987 supernova, 160,000 light-years away, was detected by the facilities of that era. 3 detectors caught a combined total of roughly 24 neutrino events. 24 particles from a star 160,000 light-years away earned a Nobel Prize and confirmed the core collapse model of supernovae in real time. Betelgeuse is 230 times closer. The neutrino flux at Earth from a Betelgeuse collapse would be roughly 50,000 times more intense than the 1987 event. The current detector network would register thousands of signals in a window of about 10 seconds. Every major facility on Earth would be simultaneously flooded. The critical thing is timing. Neutrinos escape at the exact moment of core collapse in the first fractions of a second. The light from the supernova requires the shock wave to travel outward through hundreds of millions of miles of stellar gas before reaching the surface and beginning to radiate outward. That process takes hours, possibly a day. That gap is a warning window. When the detectors fire, automated alert systems activate within seconds. Pre-programmed telescope response systems swing instruments toward Orion automatically, before the sky changes, before any human eye notices anything different about the star. This system, called the Supernova Early Warning System, exists right now. It is active. It connects neutrino detectors across multiple continents in real time. It was built specifically so that the first moment of the explosion breaking through the stellar surface, never recorded in real time before, would be captured while it happens. Then the light arrives. At peak brightness, Betelgeuse in supernova would shine as bright as a crescent moon. That number comes from well-established supernova physics applied to Betelgeuse's known distance and estimated mass. A crescent moon is bright enough to cast real shadows, bright enough to navigate by an open terrain, bright enough to see your hand clearly in darkness. That light would come not from a broad disk spread across the sky, but from a single pinpoint, sitting exactly where Betelgeuse has always been. In daylight, it would be visible as a distinct point of light, something no living human has ever seen. The last supernova visible in full daylight was recorded by Chinese astronomers in the year 1054. The Betelgeuse supernova would exceed that. The peak brightness would last 1 to 2 weeks. After that, the slow fade begins dropping over weeks and months, remaining visible to the naked eye for roughly a year, detectable by instruments for decades, as the expanding remnant continues radiating across multiple wavelength bands. Every telescope on the planet would swing toward Orion. Every observatory would suspend existing programs. Papers would begin appearing within days. Billions of people who had never thought about a star would look up. The scientific data available from a Betelgeuse supernova, compared to any previous observation, would be almost incomparable in richness, with signal strengths orders of magnitude higher than the 1987 event across every measurement band simultaneously. What remains after the light fades would be a supernova remnant, an expanding shell of stellar material moving outward at a significant fraction of the speed of light, sweeping up surrounding gas, heating it to millions of degrees, glowing in X-ray wavelengths for thousands of years. At its center, one of two things. If the collapsed core ends up below roughly 2 to 3 solar masses, the quantum pressure of tightly packed neutrons halts the collapse and a neutron star forms 12 miles across, containing a star's worth of mass, spinning hundreds of times per second. If the core mass exceeds that threshold, gravity wins completely. A black hole forms. The central object vanishes behind an event horizon. For Betelgeuse, both outcomes are plausible. The star's estimated mass sits uncomfortably close to the boundary between the two. Which side the final core mass falls on depends on factors carrying significant uncertainties that current science cannot resolve. What is not uncertain is what the explosion contributes to the galaxy. The elements forged in Betelgeuse's core over millions of years of nuclear burning, along with the heavier elements produced in the explosion itself, scatter across hundreds of light years of space. That material eventually becomes new star systems, new planets. The calcium in future bones, the iron in future blood, the oxygen in future atmospheres. All of it passing through Betelgeuse on its way to whatever comes next. The star is not just a spectacle, it is a factory. And its final product is the raw material of everything that follows. There is a thought that sits underneath everything in this story, a thought the scientists studying Betelgeuse carry into every observation session and every data analysis, a thought that does not resolve neatly and does not offer the comfort of a clean conclusion. The light you see when you look at Betelgeuse tonight left that star approximately 700 years ago, not as an estimate, not as a rough approximation, as a confirmed physical fact derived from the measured distance and the known speed of light. The information arriving at your eyes right now is information about what Betelgeuse was doing in the early 14th century, the age of the Black Death, the height of the Mongol Empire, the medieval world. Every measurement ever made of this star is 700 years old by the time it reaches us. The great dimming, the surface mass ejection, the broken pulsation, the record brightness surge. All of it is ancient history by the time it arrives. The actual present-day Betelgeuse, the star as it exists in the universe right now at this exact moment, is not difficult to know. It is unknowable. The information about what the star is doing right now will not arrive here for another 700 years. No technology that exists or can be conceived within current physics retrieves information faster than light allows. This means Betelgeuse could have already exploded. At any point in the last 700 years, the the light from that explosion would be traveling toward us right now. The sky above Orion would look exactly as it looks tonight. The familiar reddish point. The belt below. The same geometry humans have used to orient themselves on dark nights for thousands of years. And the star producing that light would be gone. If the core collapsed in 1400, the light arrives around 2100, roughly 75 years from now. If the core collapsed 50 years ago, the light arrives 650 years from now. Whatever Betelgeuse actually is right now, in the real present of the universe, whatever it has already done or is about to do, we will find out when the light arrives. Not one moment sooner. And somewhere between that thought and the instruments still running in the dark, the scientists are awake.